Okay, so chapter 5, dealing with Newton's laws. Okay, and then first coming out of section 5.1, over some terminology again. So we were talking about last time that forces are just an interaction between two or more objects. So let's write that down again and add to that definition. And that interaction can be a gravitational interaction, electric interaction, electromagnetic interaction, the strong force that exists in the nucleus, any type of force, any type of interaction that we can call a force that exists between two or more objects. And our notable examples are the gravitational force and the electric force. Also under force, the force is something that can cause an acceleration. It doesn't always cause one. As we learned in Newton's first law, that when all the forces are balanced together, the total number of forces, the net force in that system is going to be equal to 0. So that's a case of balanced forces. And when you have balanced forces, there is no acceleration. But in the case of unbalanced forces, your net force, you have a force that is larger than the other forces in question. So therefore, you can cause an acceleration in that case. And that's Newton's second law. So force is something that can cause an acceleration. It doesn't always happen. As I mentioned, unbalanced forces cause accelerations. Things moving. It's straight up out of a summary of section 5.1. And balanced forces, that's what we're starting off first, BFPM, balanced force particle model. So balanced forces do not cause accelerations. They keep things still. This is the case of Newton's first law, the sum total of the forces in the system, whether it be one or many, the total force is going to be equal to 0. And when those total forces equal to 0, the object is either going to remain at rest or it's going to remain at constant velocity. And we know that forces can cause an acceleration. So if they don't cause an acceleration, the object's velocity doesn't change if it was going at a constant velocity, or it remains at rest. Okay. So that's, again, Newton's first law. So the BFPM involves Newton's first law. An object at rest object moving constant velocity remains at again, this is just summary from last time, unless acted on by an outside force. That force is not equal to 0. It's going to be a force that can cause this velocity to change. And that is Newton's second law. So we're going to be staying today primarily at Newton's first, where everything's in balance. All the forces in the system will be equal to 0. So we've defined what a force is, that it's any interaction between two or more objects, and they can cause an acceleration. But in our case, we're going to look at forces that do not cause accelerations. And then there's two types of forces. One, contact force. Forces that touch objects, right? That they're in contact with the with objects. All right. So forces acting by touching your objects, and forces that require contact. And then there are the field forces that don't require contact. The gravitational force, the electromagnetic force, those are field forces. They don't require any touching. So you have an object in space and let it go, it's going to be acted on by the gravitational force and under the acceleration due to gravity, but the force that's causing it to fall is the gravitational force, and that is acting through a field. It doesn't require touching. Okay. Well, those are the basic two types of forces. Well, generally speaking, if you even know your contact forces are a special type of field forces. So, like if you put two fingers together, or you put your fingers on an object or something, the reason why your fingers don't go through the objects or your fingers don't go through other fingers is because they're being repelled on a small level by the electromagnetic force. And so that's why, when you put your hands together or whatever, you're actually experiencing a repulsion by the electromagnetic field force. And so that's another subject for another day. But for all intents and purposes, we're just going to call those forces that touch your contact forces. You hang a painting on the wall, you got a nail in the back of the painting. Well, the nail is in contact with the painting, and so we just call that maybe the force due to the nail. And then there's also a force of gravity that points downward, and that's going to be acting through a field. Gravity doesn't touch objects, they act through a field. All right. So that being said, there are, of the field forces, there are 4 different types of field forces. So mostly we're going to stay at the gravitational field force. There is the electromagnetic. Sometimes it's spliced into electric and magnetic force, but since the electric and magnetic fields are part of the same spectrum, we call it the electromagnetic force. They affect each other. So if one changes, the other one changes in the in a perpendicular direction. But okay, a strong nuclear field force. There is the weak nuclear field force. The strong nuclear field force exists at the nucleus that keeps the nuclei together. The weak nuclear force is involved in radiation. So when you have an unstable uranium isotope or whatever isotope you have, and it radiates X number of bosons from its nucleus, well, that interaction is through the weak nuclear force. So keeping things simple, the weak nuclear force is involved with radiation. We won't be dealing with the strong and the weak. And this is pretty straightforward. The gravitational force, we're going to see that that's represented by the symbol F sub G. And then electromagnetic would be F sub E for short. Gravitational force involved with masses. Okay, guys, put your cams on. Ms. Hernandez is coming in. I don't want to barking at me. Okay. So please do that. All right. Okay, so again, the 4 types of field forces. Gravitational field force, like I was saying, that involves mass interactions. The electromagnetic field force involves charge interactions, so 2 electrons, 2 protons, electron and a proton, and they have the same type of dependence, gravitational, electromagnetic, but we won't worry about the dependence between the 2 today, but just itemizing the different types, and the strong nuclear and the weak nuclear force. Okay, so our next thing I wish to talk about, we've talked about this last time, that forces are vectors. And we can see that notably last time we were talking about Newton's second law, where we had the formula, the net force is equal to mass times acceleration. So we have a vector times a scalar and produces a new vector. We know that vectors have a magnitude and they have a direction. So the same rules apply for forces as they did for acceleration, velocity, and displacement. So if you want to find the magnitude of a force, same Pythagorean sum, it's going to be made up of all the forces in the x direction, all the forces in the y direction, and we shall do the sum of the squares and square root of that to get the magnitude of the force. And the same thing for direction is just the angle as well. So inverse tangent Fi over Fx. Any questions on these definitions so far? It seems pretty straightforward. Is it familiar? I want to stop there before we go to our examples. Okay. So let's move on to our new slide here. So just going to itemize section 5.1 and section 5.2. So Newton's laws. Again, we talked about the first law already, so we should be quite familiar. Get to the second and third laws. So on the previous slide, we defined it. So this is sometimes called the law of inertia. And let me explain what inertia is. Inertia is a tendency to resist any type of force. And it totally depends on the mass of your object. So let me just talk about that verbally here. Let's mute the mic there. Okay, so inertia is the ability of an object to resist changes in its motion. So for example, if you have a tennis ball and you have a 2-ton truck and you apply 2 newtons of force to both objects, well, the 2-ton truck is going to be more resistant to that 2 Newton force because it has more mass than the tennis ball. The tennis ball can move easily because it's less massive. So it doesn't have as much inertia. Now, the word in inertia, the root word is inert, meaning to stay still, to resist the change. Inertia is the state of being of resistance. So when you say inertia, it is basically this: the ability of an object to resist changes in its motion. It's the state of being, it's a state of resistance based on its mass. So the more mass an object has, the more inertia that it has, and the more resistance it will have under any given force. That makes sense.
Is it only based on mass?
Yeah. You know, for no real argument, I mean, because everything in physics has a little grain nuance to it, but basically mass, yes. So, and let me continue.
Wait, why doesn't it involve speed?
Because if we're resisting a change to a force, we're not going to be concerned with the speed of the object. It doesn't, once the object gets in motion, then based on like back to the example, if we have a 2 Newton force and that tennis ball gets moving, then that inertia, the inertia of the tennis ball is less than a 2-ton truck because it's easily moved. So it's not that inertia has a dependency on the speed. It's a dependent, it totally depends on the ability to get it moving in the first place. So speed is irrelevant. Yeah. So
Thank you.
yeah. So so again, sometimes we just have to look at the words themselves, and we can extract so much information from them. Look up the word inert. If something's inert, you're not going anywhere. There is a let me finish writing this down. I'll give an example of that. The more mass and object has, more inertia it has, therefore resistance, more resistance to a force. Okay. And way back in the day, I established this equation. More inertia equals more mass equals more resistance. So you know that intuitively. You're going to need a large amount of mass to get the 2-ton truck, a large amount of force to get the 2-ton truck moving versus the tennis ball. That's it. That's intuition. You know that intuitively. And that's because of this property called inertia. So if there is not enough outside force to get that 2-ton truck moving, it's going to remain inert, remain at rest, unless a large enough appreciable force gets it moving. Now we have a situation where we have accelerated it from 0 velocity to some other non-zero velocity. And now at that point, we have entered the realm of Newton's second law. But if it remains at rest, it's inert, and the net force is equal to 0. It's in balance. So Newton's first law, AKA, right? That's long and short of that. Okay, anything else I want to say about that? All right. Again, we've seen this. Net is equal to 0. And this net force can be made up of many forces to equal 0. F net is equal to F1 plus F2, superposition of forces to make a total force. Well, if this is true, then all these forces together, no matter what direction they're oriented, are going to be equal to 0. And that's what we're going to be dealing with when we do sample problems involving objects in balance. Because the total of anything is made up of its parts. Superposition to make the net, and that net being 0. And when the net force is equal to 0, the object is either at rest or moving at a constant velocity. The acceleration is equal to 0. It just cruises along. Okay. So hopefully you got all that. All right. Anything you missed, let me know. So section 5.3, we deal with the concept of mass. And mass is really just the amount of matter in an object. The units of mass, we already know, kilograms, grams, kilograms, any version of gram. Our typical unit is the kilogram. Mass is different from weight. We're going to see that weight is just mass times gravity. So when you weigh yourself, the scale is measuring your mass multiplied by gravity, because the Earth is trying to accelerate you to the center. Mass times the acceleration of gravity, and the scale measures how much that is, how much your weight is. So I have a digital weight scale. I put it in kilograms. because we normally deal with that. So as we're talking, weight measures the force due to gravity. Weight itself is not a vector, even though we measure it in terms of a force. So let me make the distinction when I get there. But weight is the scalar quantity of the force due to gravity. So write that out. So weight measures the force due to gravity, and which is denoted by F sub G. And this symbol here, we call the force due to gravity. The force due to gravity is the vector, because that's going to always be pointing down to the center of the Earth. So this force due to gravity is always going to be negative, but the scalar is the weight, right? Like velocity is a vector, but the scalar is the speed. Same thing goes here. Okay, so F sub G is going to be equal to, well, technically negative mg, where g is the acceleration of gravity. Okay, so that whole thing is your force due to gravity. This quantity inside is your weight. Understand that? Very similar to velocity is, let's say we have a calculated velocity is a positive 15 meters per second. Well, this whole thing is your velocity 15 meters per second to the east or north, but then this number inside is your speed. I just went 15 meters per second. Okay, but you don't know what direction. This is your speed. But the whole thing is your velocity. Just like here, the absolute value is your weight, and the whole term is your force due to gravity. Okay, so we'll stop at Newton's second law. So let's go to an example problem here.
What letter do we put for weight?
We can just say FG, because this F sub G is basically going to measure force due to gravity and your weight. So it's the same thing. Okay. So this distinguish it from W, which we commonly associate that with work. And that's going to be a new concept down the line. Okay, let's say that we had a book on a table here, and we're going to represent the book by a particle, because as we do all objects. Now, referring back to the packet that we were talking about last Thursday, there are going to be two forces, at least in this diagram. Oh, okay. So scrolling up, is this fine? I just, anything that's you missed, let me know. I can go back. Okay, so this is a book on table. And if we go back to our packet, we were talking about different types of forces all together. We're talking about the normal force, the friction force, the gravitational force, tension, different types of forces. So as this book is resting on a table, we know that there is at least a normal force from the surface, because a normal force is always perpendicular from any surface. So here's our table, which is horizontal, and it's just denotes that the stuff underneath. And then the normal force on this object would point perpendicular up from the surface. 1 second. Okay, sorry about that. Okay, so we're object on table. We have a normal force pointing perpendicular up from the surface. And then that's our contact force in this case. And then there's another force due to gravity that's always going to point towards the center of the Earth. Now, this is a quick example of a free body diagram that we're going to go even more detail when we get back to our packet. But what we're doing here is we're taking an object and we are labeling all the forces that are acting on this object. So what a free body diagram does is it looks at an object, frees an object up. So basically, we are looking at one free body, if you will. And in this case, it's a book on a table. So we're looking at one free body. To determine all forces acting on it. So book on table. We have a normal force pointing perpendicular from surface, force due to gravity or weight pointing down. But technically speaking, if we're talking about the forces, we're going to call this the force due to gravity. We know that the scalar part of that is the weight, but we don't, that's semantics, that gets trivial. So we're just talking about forces. The x direction, in this case, there are technically forces there. You could talk about air resistance, but for the most part, we're going to ignore air resistance in all of our problems until we get there. You could make an argument that there's friction, but friction is going to involve some sort of push and pull, and we'll be dealing with friction down the line. So to keep things simple, if you just have an object at rest on a table, in this orientation, look, it's just right there on the table. The table is not tilted or anything. The only forces that exist are in the vertical or y-axis. Book on table, normal force points perpendicular up from the surface, and we have the force of gravity. Just for perspective, we can have an x-coordinate, xy plane here. All the forces in this case are in the vertical axis. So that's the pictorial form of the free body diagram. Now, if we were curious in how to represent that mathematically, we know that the total forces in the system, in this case, equal to 0. But what are the forces in this case that make it 0? Well, it's all the forces in the x-axis and all the forces in the y-axis. F net is equal to F sub x plus F sub y equals 0. This equation here, this tells me that I have forces, the net force, the total amount of force is made up of all forces in x and in y. Just like if we went back to our vector discussion, we were talking about the resultant vector is equal to a and b. The logic is the same here. If you recall, some arbitrary resultant vector R is equal to A plus B. This here is the physical representation of this abstract concept. I no longer have some weak, arbitrary R vector. I have a net force. And A in this case is Fx, and B in this case is Fy. I've already established that there are no forces in the X direction. So I can just take it one step further and say, all the forces in the Y direction are made up of the normal force and the force due to gravity. Now force is a vector. So we must be careful on our directions as we write this equation. So Fy would be positive Fn or just Fn. Fn minus Fg equals 0. We know that the net force is only equal to all the forces in the Y direction. All of that is going to be equal to 0. Fx, there's nothing. There are no forces in the X direction. So in this real, hopefully simple case, the net force is just all of the forces in the vertical direction. And they're made up of the normal force minus the force due to gravity. Those forces together, when you add them, they equal 0. So the net force in this scenario is the forces in the Y direction, and they all equal 0. I can just write this in. So F net is equal to Fy, which is equal to Fn minus Fg. Does that make sense? Any questions? Fx is done. There's nothing happening in the X direction. What this allows us to do in this case is to find out what the normal force is, right? It's going to be equal to Fg. Since we know that Fn minus Fg is equal to 0, and the question says, okay, what's the normal force? Well, Fn is equal to Fg. So therefore, the normal force, and we know the equation for Fg, that's equal to mg. And let's say that the textbook had a mass of 2 kilograms. Well, we can get the numerical value of the normal force. 2 kilograms times 9.8 gives me 19.6, and forces are measured in newtons after Isaac Newton. 19.6 newtons of normal force. So the normal force, 19.6 newtons upward, and it's exactly equal to the force due to gravity down. 19.6 minus 19.6, 0. We have shown mathematically that the forces are equal to 0 to verify the concept of forces that are in balance must equal to 0.
So that means that the table is experiencing 9.6 newtons of force at all times while it's on rest.
In this case.
Yeah.
Exactly, yeah. So it's like equal and opposite forces. That's a good question, because not only do we see this as an example of Newton's first law where the forces are equal to 0, the table pushes up on the object at 19.6, and the object pushes down on the table at 19.6. Well, let me be a little bit more accurate with that. So if we're just looking at the book and the table, Newton's third law says, for every action, there's an equal and opposite reaction. If the table pushes up at 19.6, then the book pushes down on the table at 19.6, equal and opposite. And since they're, well, equal, nothing moves. There's no net force. Now, if I came along and pushed down on the table, giving more force on the table, and if the table had a tendency to like fold or something, then the table falls down. But also back to your question about the table, does the table always experience 19.6? Well, that depends on the table's interaction with the ground, and that's another issue. So if the table's weight is 19.6, the table's going to have more mass than the book. But if its weight was 19.6, it would push down on the floor at 19.6, and the floor would push back up at 19.6. But the table is more massive, so it's going to actually push down on the floor with more force because it's got more mass. Okay, so I want to stay with that for a second and make sure you get that, because I want to go to another example that deals with hanging signs and stuff. So get that down. I'll be right back. Okay, go back to older textbook here. Okay, so here's an example of a light fixture being hung on the ceiling by two wires. So I have a situation here, and then, okay. So the problem says, find the tension in the two wires that support the 100 Newton light fixture. So anytime it uses a force to describe an object, this automatically is its weight. So the force due to gravity, which is always negative in the negative y-axis, that's going to be negative 100. The weight is 100, but the force due to gravity is negative 100. It's important to make that distinction. In this problem, it says that their angles with respect to the ceiling are going to be 40 degrees. So the tension is going to be the same, but you can intuit that or not. We're going to show that. Also, back in the packet, we were saying that like we have these two wires going to the ceiling, then the tension force is always going to go away from the object in question. So the object in question is the light fixture. We're going to see the forces that are acting on this object in a free body diagram. So right now, this picture is both the picture and a free body diagram, but I'll isolate it just to clear things up a little bit. Okay, and its weight is 100. Force due to gravity, though, negative 100 newtons. Okay, so let's just make a clear free body diagram of the object. We want to isolate. We want to free this body and identify all the forces acting on it. We have tension here, tension there, and force due to gravity, or negative Fg. We know that the net force in the system is going to be made up of all forces in the x direction and in the y direction. And we know that the sum is going to be equal to 0. So we don't have to do a Pythagorean sum. We know it's going to be 0. So we're interested in what are the forces making up 0, so that we can find out stuff like tension and mass and stuff. Okay. So free body diagram. So anytime you got the picture, the first thing you want to do is make your free body diagram. So FBD. Then after you make your free body diagram, you want to identify all the forces in the horizontal and the vertical plane, the X and Y plane, X and Y axes. So first thing, FBD, set up a coordinate system so you can identify all forces in the X and Y directions. So what do I mean by that? You have your free body diagram here. The tensions are going towards the ceiling, going away from the object. The coordinate system here is just going to be a normal coordinate system. You're going to have y-axis there, x-axis here. So based on this coordinate system, this is going to allow you to isolate all forces in those axes. So you can already see that the tension forces are off axis. Those two tensions, those two T's, don't exist on the X or Y, but there are parts of those tensions that do exist in the X and Y direction. Can anybody tell me what those parts are?
Sine and cosine of t.
Yep, exactly. So here's 40 degrees, and so tension's at an angle. All forces like tension at angles have two parts. So it's going to be made up of the cosine part here and the sine part there. This 40 degrees is this 40 degrees on the interior. And this part is going to be positive t cosine theta because it's along the positive x-axis. This part of the t is going to be negative t cosine theta. This on the negative x-axis. So, and this FG is negative because it's on the negative y-axis. And then these two sine parts, oops, those are going to be on the positive y-axis. So we have two along the positive y plane, one along the negative y plane. Can everybody see that these tensions will cancel out? The t cosines, positive t cosine and negative t cosine. Those angles are equal. But let me set this all the way up. So again, my net force is going to be made up of everything along the x and y planes. You know that everything together is going to be equal to 0. F of x, all the stuff in the x direction will equal 0. Everything in the y direction will equal 0. There's no movement at all. The object at rest will remain at rest. F net. So this is what I like to do first. And of course, you can put your own touch on it, your own personality into the solutions, as long as you get the right answer. But I like to identify everything happening along the x-axis, and then the y-axis, and add them together, because that's what they essentially are going to do. They're going to add together to get the net. So everything along the x-axis, I'm going to have one positive t cosine, okay, 40 degrees. Yep. And the other one is going to be the negative x-axis, t cosine 40 equals 0. You can already, even without using your intuition, you can see that those forces in the x direction will be equal. They'll cancel out. So everything in the y direction. Let's go back and make sure. So I have a t sine component here. If this is t cosine, this is t sine. Let me distinguish these real fast. Okay. So again, this wire had tension T, and this is negative T cosine. This will be T sine. Oops. Sorry about that. That's T sine theta here. And here's another T sine theta. So along the positive y-axis, I have a T sine and I have another T sine. So I have 2 T sine of 40. And then is that everything? Nope. I'm always going to have a force due to gravity. So it's going to be a negative FG in all of your problems in some form. And that equals 0. So everything everywhere equals 0. X, Y, total. So let's deal with the x-axis first. So that's my first deal. I know it's going to be F net. You know, the reason why I like to do this because just to show that this is a system of equations that at some point you're going to be able to cancel T's out in order to get other stuff because you know that in principle that this is just a system of equations. Okay, so T cosine 40 equals T cosine 40. I mean, that's just, you can't do anything with it. They're equal. 1 equals 1. Okay. Nothing you can do. You can't solve for tension using the x-axis. And yeah, that's another thing. So you can take one of the one set of forces in one axis to solve for what you need to solve for. In this case, you can't solve for the tension using the values in the x-axis. So the only option you have is the y-axis. So let's deal with that. So 2t sine 40 is equal to the weight, is equal to Fg. Okay, well, what did we say that the weight was? It's 100 newtons. So it's going to be 2t sine 40 equals 100 newtons, and we can solve for t easily. Okay, that'll be t equals 100 newtons divided by 2 sine of 40. And we have our answer. Solve that out. So we have 100 newtons divided by 1.29-ish. It comes out to be 77.5 newtons. So the tension in both wires is 77.5. The angles are the same. So that's something you should know from geometry, but if not, you can prove it that they're equal. Any questions on that? Any questions on any of those steps? Because the method is very important, and it doesn't matter. As these problems will get crazy because now you're gonna have objects on ramps, and so we're gonna have to just break them down. We're gonna have to, change our orientation of the of this coordinate plane, but the logic remains the same. First thing you want to do, draw your free body diagram on the object in question. Set up a coordinate system so you can identify all the forces in the X and Y directions. Why is that? Because the net force is equal to everything in the X and the Y direction. Then set up your system of equations. Set up everything in the X direction and in the Y direction. Signs are important, or else you say plus and things get crazy. You get a t equals negative 77.5. Well, you know intuitively that it's got to be positive 77.5, but you know you can usually have the math work out the correct sign. Okay, one last example if that was okay. Okay, so example 2. So I have this bird feeder, and I have a rope that's at 60, the other one's at 30. And in this okay, so the bird feeder is here. So why don't you guys right now, so find tension in both wires. For this 150 Newton bird feeder. Okay, so that would be the weight. Take about 5 minutes to do that. You don't have to break out. Go ahead and take your time. Follow the method. Free body diagram. Get your coordinate system. In this case, everything is pretty simple. We have x-axis, y-axis like this. So it's your job to put everything, to label all forces in the x direction and y direction. Different angles, so the tensions will be unequal. So we're now at T1, T2 cos 60 over cos 30. So P1 will be something times T2.
Can you scroll up a little bit?
Yeah. Right here. Divided by okay, so this here should be 0.577 T2. And this is what you can do. You can replace your T1 into this part. And so everything's in terms of T2. Solve for T2, then back substitute and solve for T1. I know we're running up on time. Let me just tell you what's going to be on the exam.